Dear students, in this lecture we discuss Karl Pearson's coefficient of correlation. In previous lecture we have seen definition of correlation, use of studying correlation and types of correlation. These are various methods of studying correlation: graphical methods, scatter diagram method, simple graph, mathematical methods, Karl Pearson's coefficient of correlation, small r, Spearman's rank correlation coefficient, capital R, concurrent deviation method, method of least squares. From this, today we shall see Karl Pearson's coefficient of correlation, R, small r. Karl Pearson has given the mathematical formula to measure the correlation between two variables, which is based on the following assumptions. There is linear relationship between two variables. There is cause and effect relationship between two variables. It is defined as Karl Pearson's coefficient of correlation between two variables x and y, denoted by rxy or simply r, is given by r is equal to covariance between x and y divided by sigma x into sigma y, where covariance between x and y is given by this equation, and sigma x is standard deviation of x, sigma y is standard deviation of y, and n is number of pairs of observations. The value of r denotes the magnitude of correlation and its sign denotes the direction. Now, as in this formula covariance between x and y is used, it is also called as covariance method. Now the above formula can be written as, if we denote small x is equal to x minus x bar and small y is equal to y minus y bar, that is the deviations from respective means, then that above formula can be written as r is equal to summation of x into y divided by n into sigma x into sigma y. Again, in terms of deviations and sum of squares of deviations, the formula becomes r is equal to summation of x into y divided by root of summation x square into root of summation of y square. This formula is known as product moment formula. Again, there are two different methods. So if the means are not integers, then we use assumed mean method, and the formula is like this: r is equal to n into summation of dx into dy minus summation of dx into summation of dy divided by root of n into summation of dx square minus summation of dx bracket square into root of n into summation of dx square dy square minus summation of dy bracket square. When the x and y values are very small, so we can use actual observation method, r equal to n into summation of x into y minus summation of x into summation of y divided by root of n into summation of x square minus summation of x bracket square into root of n into summation of y square minus summation of y bracket square. These are the properties of Karl Pearson's coefficient of correlation R. The first property is Karl Pearson's coefficient of correlation always lies between -1 and +1. That is -1 less than or equal to R less than or equal to +1. Second property is the Karl Pearson's coefficient of correlation R is unaffected by change of origin as well as change of scale. This third property is important regarding to the correlation coefficients and regression coefficients. Karl Pearson's coefficient of correlation R is equal to the square root of product of two regression coefficients, that is R is equal to root of bxy into byx, and it has the sign of bxy as well as byx. In other words, R is the geometric mean of two regression coefficients. And the last property is Karl Pearson's coefficient of correlation is pure number free from units. Let us see merits and demerits of R. Merits. Karl Pearson's coefficient of correlation gives the numerical value of the correlation along with the direction of correlation. It is useful for estimation. In demerits, the value of R is unduly affected by extreme values. The computation of the value of R is sometimes tedious job. The value of R can be calculated only if the data is numerical. It cannot be calculated for qualitative data. Great care is needed while interpreting the value of R. And last one, it cannot be calculated when there is no linear relationship between the variables. Now let us see how to interpret the value of R. The general rules to interpret the value of R are as follows. If R is equal to plus 1, then there is perfect positive correlation. If R is equal to minus 1, then there is perfect negative correlation. If R is equal to 0, then there is no correlation. If and 8 less than R less than 1, then there is high degree positive correlation. And if 0 less than R less than zero point 0.4, there is low degree positive correlation. All the points regarding to interpretation of R can be summarized in the following table as well as diagram. So if the magnitude of R is between zero point 0.8 and 1, there is very strong correlation, that is high, very high correlation. If that magnitude is between zero point 0.6 and zero point 0.8, then there is strong correlation, that is high degree correlation. If the magnitude is from zero point 0.4 to zero point 0.6, then we say that there is moderate correlation. If the value is zero point 0.2 to zero point 0.4, then we say there is weak correlation, that is low correlation. And if the value is 0, between 0 and zero point 0.2, we say that there is very low correlation or no correlation. Now, for direction, we may refer this diagram. So when R is equal to minus 1, there is perfect positive correlation. When R lies between minus 1 and minus zero point 0.8, there is high degree correlation. Similarly, when R is equal to 0, there is no correlation. And when R is equal to plus 1, there is perfect positive correlation. And when R lies between zero point 0.8 and 1, there is high degree positive correlation. Now let us see the numerical problems based on R. So this is the first problem. Find the correlation coefficient between X and Y from the following data. So they have given the values of sale and profit, and asked to comment on your result. So here n is equal to 10. Summation of mean of X is equal to 20 and mean of Y is equal to 16. As both the means are integers, we may use the formula regarding to the deviations from respective means. And for various sums and sum of squares and sum of product, we prepare this table and obtain the sums. Summation of X is 200, summation of x minus x bar, that is small x, is equal to 0. Summation of small x square is 30. Summation of y is 160. Summation of small y is 0. Summation of y square is 108. And summation of x into y is 35. And here the formula is r equal to summation of x into y divided by root of summation of x square divided by root of summation of y square, where x and y are deviations from respective means. By substituting these sums in this formula, so and by simplification, we have r is equal to 0.6148 with positive sign, and therefore the interpretation is, and there is positive correlation between sales and profit. Let us see another example in which the means are not integers. So calculate Karl Pearson's coefficient of correlation for price and demand values. So here they have given n is equal to 7 number of pairs of observations. Here x bar is 17.58 and y bar is 13.14. Now as both x bar and y bar are not integers, so we take the assumed mean for x as a equal to 18, integer near to this 17.57, and b, that is assumed mean of y values as 13, that is the integer near to 13.14. So by taking a is equal to 18 and b is equal to 13, so for various sums and sum of squares and sum of products, so we prepare this table. After summing the values, we have summation of dx, that is summation of x minus a is minus 3, summation of dx square is 89, summation of dy equal to 1, summation of dy square is 51, and summation of dx into dy 66. The correlation coefficient for assumed mean method is r equal to n into summation of dx into dy minus summation of dx summation of dy divided by root of n into summation of dx square minus square of summation of dx into root of n into summation of dy square minus square of summation of dy. So by substituting the respective sums and by simplification we have r equal to minus 0.98176. As the sign is negative, there is negative correlation, and as the magnitude is 0.98, there is high correlation. Therefore final conclusion here is there is high negative correlation between price and demand. Let us see one example where the values of x and y are very small. So here calculate Karl Pearson's coefficient of correlation for this set of IO observations. So as x and y values are very small, to have various sums, sum of squares and sum of product, we prepare this table: value of x, x square, value of y, y square, and the product x into y, and we obtain these sums. So in this case, the formula is r equal to n into summation of x into y minus summation of x into summation of y divided by root of n into summation of x square minus square of summation of x into root of n into summation of y square minus square of summation of y. So by substituting these sums in this equation, we have r equal to 5 into 72 minus 22 into 23 divided by root of 5 into 114 minus 22 square into root of 5 into 163 minus 23 square, and after simplification we have minus 0.9309. As the sign is minus here, there is negative correlation, and as the magnitude is 0.93, that is there is high degree correlation. Therefore the final conclusion is there is high negative correlation between x and. In the next lecture, we shall discuss Spearman's rank correlation coefficient, capital R. Thank you. Thank you very much.